Okay. Hi everyone. So I'm going to talk about the sample complexity of optimizing a convex function, and this is joint work with my advisor, Johan Singer. So in traditional optimization, we usually give in value query access to a function, and the goal is then to minimize or maximize this function. But sometimes we might not know this function, and so in the end we only have access to sample data from this function, and in this case, we might usually just learn this function first. So learning and optimization have both, of course, been heavily studied, but usually always separately. And here, in this case, we see that the quality of the learning is, of course, going to affect the quality of the optimization. So in this talk, the main question I want to explore is, can the convex function be optimized from training data? So let me be a bit more precise by what I mean. The unknown function I'm going to consider is going to be a convex function. My input is going to be samples, which are points in the unit cube, and their exact value according to the function. And my goal is going to be to minimize this unknown functions from the samples. So what's the most intuitive approach that you would think to solve this problem? You would first learn the function from the sample data, and then optimize this learned function. But as we're going to see, this can be arbitrarily bad. If you consider this simple example for the convex function f, and where we have only samples that hit this flat region, then if we use, for example, just the empirical risk minimization learning algorithm, a reasonable candidate learner is just this flat function. But for this flat function, x equal to 0 is a minimizer. And for this function, this solution is arbitrarily far from the true minimum. So we just saw that this approach to first learn the function and optimizing it can be arbitrarily bad. So what we want to do here, we need to skip the middleman. If we want to understand if convex function can be optimized from data, we need to ask directly, can we optimize it from this sample data? So to make this, so now we can introduce the model formally. And this optimization from sample model was previously introduced in the context of submodular optimization. So we say that the cluster function is optimizable from samples over some distribution. And here the input is going to be the same as in learning. So we're going to be given polynomially many ID samples from some distribution. And the output we want is the same as in optimization. We want to find a point that's close to the minimum. And here we're going to consider additive approximation. So as we will see, there are some natural classes of function that can be optimized from sample. So here the question is not, is this possible, but for which classes of function can we optimize from samples? So in this model, we have like the same input as in learning. We have the same output as in optimization. So one might hope that if the function is both learnable and optimizable, then it should be optimizable from samples. So in this talk, I will ask the following question: are Pratt-learnable convex function optimizable from samples? So now we present the main result. So our main result is an impossibility. So informally, the number of samples needed from any distribution is exponential to get any desirable approximation. And this is even if the function, the convex function, is learnable. So to be more precise, we show that there exists a class of Cohen functions which we show is Pratt-learnable, for which no algorithm can obtain a 1/2 approximation. So again, here it's the convex functions that are bounded 0, 1. And we show that it's for this impossibility for any reasonable number of samples drawn from any distribution. So since, again, it's convex function bounded 0, 1, there's a tight trivial upper bound. If you just consider the center of the unit cube, by convexity, this is a 1/2 approximation. So some important applications of this result is that learnability and optimizability do not imply optimizability from data. And another one is that this implies that in general, it's impossible to obtain any guarantee when you're optimizing a convex function that was learned from sample data. So now I will quickly give a very high-level overview of this impossibility result. So what is this class of convex functions that are hard to optimize from samples? It's actually pretty simple. It's just the maximum of two linear functions. So very informally, to see the hardness, consider these two linear functions to be random linear functions. So here, importantly, we're going to have a negative epsilon term. And so due to this negative epsilon term, with high probability, all of my samples, their value are going to be given by the second linear function. And so what this is saying is that if all of these samples are equal to the second linear function, then I'm not learning any information about this first linear function. And so, and this is where the hardness comes from. And it's impossible for the algorithm to learn any information about this first linear function. Okay. So this concludes a very high-level overview of the impossibility of optimization from samples for the class of function. So we also show that this class of function is pack learnable. And so the main idea is to combine a classification step where we first given a point, we classify it on whether which of the two linear function it's going to be equal to. And then we use linear regression to learn each of these two different linear regressions, each of these two linear functions. So here, main difficulty for the learning is that when I observe samples, I cannot observe the labels for the classification. When I observe a point, I don't know if its value is given by the first or the second linear function. So we also give impossible lower bound results for optimizing from a reasonable number of samples for also Lipschitz convex and strongly convex functions. And so quickly before concluding, let me just mention some related work that was for some modular functions. So we also showed that for some modular function, some strong low bound for optimizing some modular function from samples. And so here the conceptual difference is that for some modular functions, we have a much weaker learnability and optimizability guarantees than for this class of convex functions. And on the technical level, this and possibly the hardness constructions are very different because this result is for constraint optimization, whereas for us it's for unconstrained optimization. But on the other hand, on a positive note, if the submodular functions have bounded curvature, then we obtain a positive result. We obtain a tight multiplicative constant factor approximation. So to conclude, we studied the question of optimizing a convex function in cases where we do not know this convex function, but we have access to simple data from it. We show that it's impossible in these cases to optimize the convex function from samples, from a reasonable number of samples, even when the function is learnable. And so I think there's two different avenues of work that are interesting for future work. So the first one, of course, is which functions can be optimized from samples, so which additional restrictions do we need to be able to optimize these functions from sample. And the other one is, are there some different notion of optimization from samples that would allow to get some good approximation? So maybe some data-dependent optimization from sample, or maybe allowing some adaptive sampling from samples. Okay, and this is it. Thank you.
Questions?
Yeah. So how does your result in terms of this P-max learnability of the modular?
Yeah, so P-max, sorry. Yeah, so how does this differ from P-max learnability?
Yes.
Yeah, so P-max learnability is just an extension of pack learnability for some modular functions. So it would also fall in the same category where we see that all of these functions, they are learnable. So P-max learnable also says that these functions are learnable, but it does not say anything about the optimizability. It just concerns the learnability. Yeah.
Yes.
So can you comment, how did you get the dimension to 1/3?
The which one?
Why do you get dimension to 1/3?
And to the 1/3?
Yes. Just where does it come from? I mean, it seems like you just analyze that example, like two linear functions, so you only need to analyze the probability that they all fall into the regime regime or
Yeah, so this is mostly just from like standard concentration bounds. So if you just, it's mostly from standard, so should I repeat the question? Or? Yeah, it's mostly from standard concentration bound, like Chernoff type, and you get this into the method. Yeah.
Okay. Any further questions? If not, then we'll wrap up the session, and let's thank Eric again.